This PowerPoint will help you with inequalities. We use inequalities to indicate that two quantities are unequal. These are the four symbols we use when we are dealing with inequalities. One thing to keep in mind, when you have something that is greater than or equal to, or less than or equal to, you have to remember to put the bar underneath both of those symbols. Here are some inequality rules we need to know. For the most part, we treat inequalities just like we would an equation. The only difference is equations have the equal sign, and inequalities have the greater than sign, less than sign, greater than or equal to, less than or equal to, just like we talked about in the previous slide. Adding or subtracting the same number on both sides of an inequality does not change the solution, just like we do in an equation. In this example, when we have x plus 2 is greater than 4, subtracting 2 from the left side to the right side does not change this inequality. We will still have x is greater than 4 minus 2, which is 2. The next rule is multiplying or dividing by the same positive number does not change the solution once again. So in this example, if we were to divide the left side by 5 and the right side by 5, because whatever we do to the left, we have to do to the right, just like in an equation, our 5s would divide to 1, and we would be left with x is less than 10 divided by 5, which is 2. We can see that multiplying or dividing by the same positive number does not change the solution, just like it doesn't in an equation. Now, we saw that multiplying or dividing by the same positive number does not change the solution. However, when multiplying or dividing by the same negative number, it does change our solution. Whenever we have a negative number and we are dividing it or subtracting it to the other side, we need to reverse our inequality sign. For example, greater than would become less than. In the example below, negative 2x is less than 4 if we happen to divide both sides by 2. Dividing both sides by 2, a negative 2. Our negative 2's would divide to 1, and we'd be left with x is less than 4 divided by negative 2. Now, since we divided by a negative number, we need to make sure our sign changes. So our sign would then become x is greater than a negative 2. Next, we're going to look at solving an inequality that's a little bit more challenging. Our same rules apply as they would for our equation. We still want to isolate our variable x. So in the following problem, our first step would be to distribute the 3 to both pieces. When we do this, we get 6x minus 27 is less than 9. Now, our next step will be to add 27 to both sides. When we add or subtract a number, we know that the sign does not change because of our rules of inequalities. Adding 27 to the other side gives us 6x is less than 36. Our last step to isolate our variable x will be to divide both sides by 6. When we have 6x less than 36, dividing by 6 on the left side cancels to 1. When we divide 36 by 6, we get 6. Now, since we divided by a positive number, we know our rules say that our sign will not change, so x will still be less than 6. Now we're going to look at x less than 6 in a little bit of a different way. We're going to look at it using our interval notation. Interval notation is a way we can write our inequalities to show an answer in a simpler form. A couple things to remember. When we have an inequality with a greater than or equal to, we will always use brackets. Our brackets will always be used also with when we have less than or equal to. If there is just a greater than or less than symbol, we will always use our parentheses. Another thing to remember, if a number is less than 6 in our solution up here, we are going to be able to use our infinities. We will have a negative infinity or a positive infinity. Whenever we have infinities, we also want to remember that they always come with parentheses. So how we would write x is less than 6 in our interval notation would be parenthesis, negative infinity, all the way to 6, other parenthesis, because we just have a less than symbol in it. We know that it goes off to negative infinity because x is less than our number, so that is saying it is going off into negative infinity. As we know, we always want to use parentheses with positive and negative infinity. Our answers below are written in interval notation. If x is less than 6, we know that x will be going off into negative infinity, and then we know there's 6. We will have a parenthesis around both pieces because it is less than and because we have an infinity. Our next problem, x is greater than or equal to 12, we know we will have a positive infinity because it is greater than a number, and we know that our infinities always have parentheses, and we know we always have 12 because that is our answer, and 12 needs a bracket because it is greater than or equal to. Our last example, negative 5 is less than x. We know that negative 5 will need a parenthesis because it is less than our x. Also, we know that since x is greater than negative 5, it will be going off into positive infinity. Whenever we have infinities, we know we must use a parenthesis. These are just some examples of how we can write our interval notation. We will now solve an inequality. Our first step to isolate our variable x will be to add 8 to both sides, leaving us with negative 12x is less than or equal to 16 plus 8, which is 24. Our next step will be to divide negative 12 from both sides. The negative 12s on the left will divide to 1, and we will be left with an x is less than or equal to 24 divided by negative 12, which we know is negative 2. Now remember, we divided by a negative number, so our last step we know will have to be to change our sign. So our final answer would be x is greater than or equal to a negative 2. Now, the next part of our problem says we need to write our answer in interval notation. To write our answer into interval notation, we know we are going to have a negative 2 in our answer. We also know we are going to need either a positive or negative infinity. Since x is greater than our number, we know we're going to use a positive infinity. Infinities always come with parentheses, and we know since our equation says greater than or equal to, our negative 2 will have a bracket. And this will be our final answer written in interval notation. Next, we're going to go over some vocabulary terms. Our first vocabulary word we are going to go over is union. Union is used when we have an or in our inequalities. If we want to show how this is done with the following inequalities on top, our first thing we would do is we would write 2, 3, 4, 5, and if we want the union, a union is denoted by that symbol. Our next word, intersection, is denoted by this symbol and is used when we see and in our equation. So for the following examples, 2, 3, 4, 5, if we had an intersection between these two, we would put the intersection symbol in between them. Some examples of interval notation using and or are below. Our first example says x is less than negative 4 and is greater than negative 7. We can also write this as, when we write it in this form, our x is in between our negative 7 and our negative 4. If this happens, we know it will not be going off into infinity or negative infinity, so it can be written as negative 7, negative 4. We use parentheses because we just have less than symbols. There are no less than or equal to. Our next example, x is greater than or equal to negative 1, and x is less than or equal to negative 3. We know our x is going to be greater than everything bigger than negative 1, so it will go off into positive infinity. If x is less than everything of negative 3, we know it will go off into negative infinity. Our negative 1 and negative 3 have parentheses because we have a less than or equal to, and greater than or equal to symbols. With these symbols, we know that our numbers are going to need brackets. Our infinities will always have parentheses, and our last thing to look at for our interval notation is our word or. When we see the word or, we know that it is automatically a union. With a union, we know we need to use this symbol, and we will put that right in between our equations. So this will be our final answer. The last inequality we're going to talk about is the double inequality. The double inequality looks like the following example. It gets its name by having two inequality symbols inside the inequality. To solve this, we are going to break it into two separate inequalities. We are going to look at the first one with a -3, having the first one this way. The next one we will look at is the 2x plus 5 is less than 7. These are the two inequalities we are going to break up for this example. And then once we break those up, we will put it together into interval notation just like all our other inequalities. We will solve these the same way as single inequalities. We will just have two potential answers. We are going to talk about absolute values now. Absolute values get their names by denoting them with these bars. Absolute values represent the distance a number is away from 0. Thus, it is always positive. So when we have an absolute value of 8, the answer will always equal 8. If we have the absolute value of -8, our answer will again always equal 8. Will there ever be an answer to this problem below? The answer is no. We cannot have an absolute value equal to a negative number because of the rule up here. We know an absolute value must always have a positive answer, so this one below will not work. The answer for this one would be no solution. If we have absolute value of x equals a number, say 3, we know, however, that our absolute value of x can either equal a 3, which is positive, or a -3. This is another rule to keep in order, not to be mistaken with this one below. Remember, if x is inside the absolute values, it will have two answers. Some steps to solving absolute values include, first, like always, we're going to isolate the absolute value expression. Once we do that, we are going to set up two equations to solve. We are going to have an equation that is going to have a negative number and a positive number, just like our example before, with the absolute values equal to 3. Our equations will have an answer equal to a positive and a negative number. In other words, for the first equation, we're going to drop the absolute value bars and solve the equation. For the second equation, we'll drop the absolute value bars and negate the opposite side and solve the equation. Negating the opposite side means turning the number to negative. And once we have done all this, we're going to want to check the solutions to make sure our answer is correct. For the equation above, the first thing we notice is that it is an absolute value expression. The first step in absolute value expression is to make sure that it is isolated. As we can see in the above equation, our absolute value is already isolated, so then we can start with the next step. Our next step to solving absolute value expressions is to set up two equations. Remember, we set up the equation and drop the absolute value bars and make it equal to the same number. The second equation then negates the opposite, which means we will set it equal to the negative of the number given, so it would be -7. Our next step then would be to solve each individually. Our first answer would be 2x plus 1 equals 7. We would do the same thing, subtract 1 from both sides. 2x would equal 6. Our next step would be to divide by 2 to both sides. We would then get x is equal to 3. Next, our second equation, we would do the same thing. Subtract 1 to both sides. leaving us with 2x equal to negative 8. We then would divide each side by 2, leaving us with x equals a negative 4. Remember, our last step is to plug both of these in to our starting equation. Our answers check out, and we know that our solutions are correct. So our solutions would be 3 and negative 4. Also can be written in brackets. Another example of an absolute value is given above. Remember, our first step to solving absolute value expressions is to make sure the absolute value is isolated. In our above equation, our absolute value is not isolated, so our first step would be to divide both sides by 6. When doing this, we then end up with our absolute value equaling a number which tells us that it is isolated. Then we go to our second step, setting our equations into two separate ones. So our first equation would be the same and have 5x plus 2 equals 52. Our next equation would drop the absolute value bars and negate the opposite. So we would have a negative 52 in the other equation. We go about solving them the same way, subtracting 2 to both sides in both equations. In the left side, we get 5x equals 50. Divide both sides by 5. We will get x equals 10. On the other side, after we subtract 2 to the other side, we get 5x equals 54 negative. Once we have this, we will divide both sides by 5, leaving us with x equal to a negative 10/8. Remember then, our last step is to check our answers and solutions to make sure that they even out in the end. And once we have checked them, we know that the answers work for our following absolute value. Here is a more challenging absolute value expression. We will start this like all the others, making sure we isolate the absolute value. To do this in the first step, we will add 7 to both sides. When adding 7 to both sides, we get 3 absolute values of x plus 2 equals our 21. Our next step will be to divide both sides by 3. These divide to 1, and we are left with the expression the absolute value of x plus 2 equals our 21 divided by 3, which gives us our 7. The next step for an absolute value expression would be to set it into two equations. Our first equation would be x plus 2 equals 7, and our second equation would be x plus 2 equals our negative 7. To solve this is the same way. We will subtract our negative 2 from both sides, giving us an x equals 5. On the other side, we would also subtract our 2, giving us an x equals negative 9. Now, however, we are not done. Our last step is to plug in our solution into the original problem and make sure our answer checks out for both solutions. Now, our last step will be to write x equals our negative 5, comma negative 9, and we can put these in a set notation.